Hi, welcome to Feynman Diagrams without QFT. In quantum field theory, there are these interesting little pictures that are used to calculate the cross section of scattering processes. And the goal of this video is to introduce these diagrams without using any messiness or any machinery of the quantum field theory. So this is just a purely mathematical video where I'll introduce how we can think about expansions and Taylor series in terms of pictures, and the ideas that we learn here will also be directly applicable to whatever people do in quantum field theory. So for for beginning, I would like to mention the prerequisites of this video, which are not very advanced. First is that you should know elementary calculus. Second is that you should know how to Taylor expand this guy. This is just 1 over whatever that number was plus x squared, whatever that number was, squared by 2 factorial, cubed by 3 factorial, and so on. And this can be written in a summation as follows: x to the power. The second prerequisite is that some sort of familiarity with the Gaussian integrals would be appreciated, but if not, we can just take these at face value. For instance, this integral evaluates to root pi. The integral that we are going to consider is as follows. It is just a little variation of this integral that I wrote above. It has this factor of m squared, which can be set to 1, but for now I'm not doing that, and there is this j. This integral is also a Gaussian. We just need to complete the square and we can evaluate it explicitly, and this can be a little exercise, but if you don't want to do that exercise, I'll just flash the solution on the screen for a moment and then we can move on to the real part of the video. Okay, I hope you have seen the solution. So let me just consider a scaled version of this integral. Let me call that z0, and that would be m over root 2 pi times this integral that I wrote above. The reason is that the solution has root 2 pi over m in it, and if I rescale it with m over root 2 pi, that would cancel out at the end. So now I am considering this integral, minus half m square x square plus jx, and as we have seen, its solution is root 2 pi over m, which would cancel with m over root 2 pi over here, times e to the power j square over 2m. So this is the explicit solution for our integral. As I said, this can be evaluated explicitly, and as a consistency check, we can see that when j is 0, this integral is 1, and on top, when j is 0, this is just this integral, and this integral is root 2 pi over m, which would cancel with this and will give us 1. So it checks out. Let me just put the j's back. Alright. Now this integral was evaluated explicitly, and now I will add another term in the integral, and the resulting integral I can call z of j. Remember, this one is called z0. Here naught refers to something that we can integrate explicitly. The integral that I'm going to write now, we will not be able to calculate it explicitly. It is of the similar form, e to the power minus half m square x square plus jx, but now there is another factor of x to the power 4, and there is also another constant here. Let's call that constant lambda, and for reasons that will be explained later, I'm also pulling out a constant factor of 4 factorial from lambda. So the overall constant I'm writing in this form. Now, if lambda were 0, we would have no problem. this integral would again just become this integral because lambda is 0, and we would be able to solve it and the answer would be this. But right now lambda is not 0, so this integral is different from z0, and the goal is to write z of j as something times this integral that we can solve, which is z0 of j. And we will do that in the following way. We will expand the Taylor series of exponential corresponding to this factor. What I mean is this. This thing can be written as e to the power lambda x to the power 4, and this exponential can be expanded using its Taylor series, which would be summation, let's call that dummy index v, and we have 1 over v factorial times lambda x to the power 4 by 4 factorial to the power v, and this whole thing we can just copy. It's still not in the form that we want it to be in because there are still these factors of x, and to get rid of these, first let me just write the summation on the other side. 1 over v factorial, all the constants that do not have lambdas in it, not have x's in it, we can write these out. M over root 2 pi, and then the integral, and then we have x to the power 4 v, because there is 4v here, and then e to the power minus half mx square over jx. Here comes the crucial step, which is this. Consider this, e to the power this minus half mx square plus jx, and differentiate this factor with respect to j. By doing that, we will get the same exponential factor, which I am writing as this, times x, because of chain rule we are differentiating against j, so this factor will be 0 and this factor will give me x, which will be multiplied. Again, if we differentiate twice against j, again we will pull the same e to the power factor out, and j differentiation will not care about x, so again same thing will happen, another x will be pulled down and we will have x square. In general, if we differentiate it, let's say 4v times, we will pull out a factor of 4v, and this is exactly what's written here, exponential of this whole thing times x to the power 4v. So which means that instead of 4v, we can write d over dj of d over dj to the power 4v, as in differentiating 4v times this function with respect to j. And this is a huge deal because now this x dependence has turned into some sort of differentiation, but there is no x here, so I can pull this outside the integral, which means I can write this whole thing as follows. And this factor in the curly brackets is the one that we know how to calculate explicitly because we did it a few steps ago. This is just our z0 of j, which is e to the power j square by 2m. So note what happened here. We removed this x from inside the integral and pulled the derivative factor outside. So we can write this as z0, this is z0 of j, which is e to the power j square over 2m. So this is our z of j. It is this factor times exponential j square over 2m, and now we can also expand the exponential factor into its Taylor series, this exponential factor. So again we will have one Taylor series here and another one here, which I will label with, let's say, L, 1 over L factorial times j square over 2m to the power L. So we have a double Taylor expansion in j. How will the terms look like? Let's say when v is 0 and L is 0. Okay, by the way, each term is labeled by v and L because one v is there and one L is there. So there will be terms corresponding to when v is 0, L is 0, then there will be a term with when V0L is 1, then there is a term when V0L is 2, and so on. Similarly, then there will be a term with V being 1, L being 0, V being 1, L being 1, and so on. And I think you get the point. Each term can be labeled by these two numbers, V and L. And now what we will do is associate with each of these terms one graph or one diagram. By graph I mean diagrams. So for example, for 2, 3 there will be one diagram, for 3, 3, 4 there will be one diagram, and so on. In general, for any V, L there will be one diagram. Once again, V, L just means a term in this Taylor expansion, and all those terms are to be added at the end. So for every term corresponding to V, L, I will add a graph, and I'll show you how that will work. First, note that this J has a power of 2L, and these 2L powers are being killed by 4V derivatives, which means that if you have a total of, let's say, 2LJs, and after differentiation 4V of those will be killed, and you will only have EJs left. For example, if you have, let's say, m powers of j, and you differentiate with respect to j n times, apart from some constant factors, we will have just j to the power m minus n. Now here is how pictures are to be associated. With each j, we consider a source and a line being emerging from that source. So for every j, there is a point from which a line is emerging. We name this point j. For example, a graph of this kind with j and j. Next, we consider what is this v doing here. So now consider 4 lines, and now consider what this derivative is doing. How I think about it is that the total number of lines that are left, or the total number of j's that are left, right now there are 8 j's, because there is one j associated with origin of the line and one j associated with the end of the line. But when we apply this operator d by dj to the power 4, when v is 1, we are applying 4 derivatives, and what those 4 derivatives will do is that they will kill 4 of these lines. A way to kill 2 lines is just to join them from one of their ends, and a way to kill 4 lines is to join 4 of their ends, like this, or drawn a little bit neatly. This should look like a 4 vertex. By 4 vertex I mean a vertex from which 4 lines are emerging. So there was a source which was a single point in space from which one line was emerging, and a vertex is a structure of this kind from which 4 lines are emerging. So V stands for vertex. If there is one vertex when V is 1, that will kill 4 lines. That means that there is a 4 vertex. So to associate diagrams with every term, this is how we do it. We need to consider any picture which is made up of lines which should have this kind of structure. This is not allowed, and this kind of structure is not allowed, and also they should follow this constraint, which means that the number of lines L and the number of vertices V, when subtracted like this, should give us total number of external lines. I will show you what I mean. Let's say I consider a certain term in the Taylor expansion with V being 0 and L being, let's say, 1. That is, in terms of pictures, I should have no vertices and I should have one line. And total number of sources, this E which stands for external should be thought of as total number of sources in that diagram. So total number of sources would be 2 times 1 minus 0, which is 2. So that graph looks like this. There are 2 sources as promised, there is no vertex, and there is only one line, which is this. Let me consider another possibility. Okay, let's say there is no vertex and there are 2 lines. Okay, this is also easy. I can just make another line on the bottom of it. This is the diagram for that. Okay, let's take one vertex example, and let's say there are 2 lines. And actually it is better if we use E, because there are 3 numbers, V, L, and there is another number E which is dependent on V and L. So we can either think in terms of V and L, which are directly manifested in this Taylor series, or we can think in terms of V and E. So it is better to think in terms of V and E, because that will make the categorization easier. Okay, let's say we have E being let's say 4, which means there should be 4 sources and there should be one vertex and there should be how many lines? We can calculate it from here. L is E plus 4V over 2. When V is 1, we will have 8 over 2, which is 4. So we have 4 lines in total, one vertex with 4 sources. The only diagram which satisfies it is this one. You see, there is one vertex right here, there are 4 sources, and there are 4 lines. 1, 2, 3, 4. These are the 4 lines. Okay, let's consider another example. Let's make it a little bit complicated. Let's say we have 2 vertices this time, and let's say again we have I don't know, 4 external points. So again we have 1, 2, 3, 4 sources from which lines should emerge. We have 2 vertices this time, and the number of lines allowed are E plus 4V by 2, as we see here. So that is 4 plus 4 times 2 is 8 over 2, which is 6. So there will be 6 lines in this graph. There will be 2 vertices, and the way to draw this, if you want to think about it, you can, but I will show you the answer. You can draw it like this. So this has one vertex and 4 lines are covered. Now I need to add another 2 lines with one vertex, but I cannot do this because that would add 4 lines and one vertex. I need to add 2 lines and one vertex. That can be done by this. Now there is only one vertex with a strange structure of 4 lines coming out of it, and there are just 2 lines here. One is this line and one is this line. So this is the graph, this is the complete graph. Okay, let me take again 2 vertices and let's say 6 sources. So again it can be this same graph, but there should be 6 sources. So total lines should be 4E plus 4V by 2. Once again, E is 6 plus 4V, 4 times 2 is 8 over 2, 8 and 6 is 14 over 2, which is 7. So there should be 7 lines. So there are 6 sources, 1, 2, 3, 4, 5, 6. There should be 7 lines and there should be 2 vertices. What can we do? Maybe we can do something like this. So again there are 2 vertices, one here, one here. From each 4 lines are emerging. There are 6 points, 6 sources, and total 7 lines are there, I think. 1, 2, 3, 4, 5, 6, 7. Correct. So these are some of the diagrams that we can associate. Okay, so once again, this thing had different numbers, some number plus some other number plus some other number and so on, and again like this. This is a double expansion series. Each number here is associated with two integers v and l. For example, this one is 0 0, this one is 0 1, and so on, like we did a little bit ago. And I'm saying that instead of numbers we can consider graphs, like I drew a little bit ago, like this one. This is not correct. Or this one. So there can be graphs that represent these numbers, and these diagrams should tell us how to calculate these numbers. And that description is Feynman rules, and the Feynman rules are as follows: that for every source j I must add a factor of j. For every vertex I see I must add a lambda, and for every line that I see, doesn't matter if it has j's at end of it or not, for every line that I see of whatever kind, I must add a factor of 1 over 2m square. This comes from here, this 1 over 2m square, because for every line there is a factor of 1 over 2m square. For every vertex v, there is a function, there is a factor of lambda. Why I have not included 4 factorial will also be clear in a moment. But okay, what else? Yeah. Okay, so let's see this graph. This graph, the number that will be associated with this graph would be j square, because for every source there is one j. For every line there is 1 over 2m square, and for every vertex there is lambda, but there is no vertex in this graph, so this is the number. Remember, this graph was associated with 0 and 1, v being 0 and l, which is number of lines, being 1. And we can see, if we look at the term which corresponds to v being 0 and l being 1, let me just write that term. The general structure of terms is like this: lambda over 4 factorial times d over dj to the power 4 whole thing v times 1 over l factorial 1 over 2m to the power l times j to the power 2l. Okay, so this is the general term for any v comma l. For v being 0, this first term will go away and only this will be there, and for l being 1, we will have 1 over 2m times j square, which is, sorry, here is a square. There should be a square, no? Yeah, I think I missed. Did I? Yeah, I missed squares here. There should be a square there, and so on. Yeah, I have missed a square. Or have I? No, yes, I have. Alright. So this is same as this. Next we can consider another graph. Let's say a graph with one vertex and two lines. This graph will look like this. Two lines are there, one this and one this, and there is only one vertex, and total E from that formula of 2L minus 4V would be 0. As you can see, there is no external source. Such a diagram is called a bubble, and the corresponding factor, because the V is 1, so I'll have d over dj to the power 4 times lambda over 4 factorial. L is 2, so we will have 1 over 2m square to the power 2. I'm calculating the factor from this, then I'll calculate it from Feynman rules, and we will see if they match up. L is again 2, so we'll have 4. So when the derivative acts on j to the power 4, I'll get 4 factorial times j to the power 0, which is just 1. So this whole thing will turn into 4 factorial, which will cancel out with this. That was the reason of 4 factorial, so that whenever we kill 4 lines at once, there are 4 ways, there are 4 factorial ways to do this. You can see it here. So I can call it j1, j2, j3 and j4, and I can sort of flip some of these. I can call this j1, this j3, this j2 and this j4. But this diagram is topologically same as this one, and there are a total of 24 ways to do this. I mean 4 factorial ways, combinatorics. So there should be a factor of 4 factorial that kills the symmetry. Okay, these symmetry factors may be confusing at first. They are not very important at the moment. I'll tell you why they are not important also. But don't care about these factors for now. The important thing is that these powers of lambdas and j's should be there. Also, so the answer here is 1 over 2m square whole square lambda j, there is no j and there is no factorial. Okay, from the Feynman rules we can see there is one vertex, so there will be a lambda, and we can see there are 2 lines, and for every line there should be a 1 over 2m square. So there will be a square of 1 over 2m square, and this is same as this. So again we are done. Okay, let's take one more, and let's take a bit complicated one, and this time we will see that the two methods are not actually matching. Okay, let's consider this one. Again, this is a valid graph because the vertex are of this form, not of this form or any other form. Again, there are 4 sources. So E here is 4. There are 2 vertices, so V here is 2, and we can calculate L either from that formula or we can directly count it. There is 1, 2, 3, 4, 5, 6 lines. Alright, so from Feynman rules we can calculate the corresponding term. It would be j to the power 4 because there are 4 sources, and there will be 1 over 2m square to the power 6 because there are 6 lines, and there are 2 vertices, so there will be a factor of lambda square. From the general Taylor series expansion, there will be a term that corresponds to a 2, 6 because v is 2 for this graph and L is 6. We will get 1 over 2 factorial lambda square over 4 factorial square times 1 over L factorial, which is 1 over 6 factorial times 1 over 2m square to the power 6 times d over dj to the power 8 times j to the power 12. Again, this will give us j to the power 4 times some factors, and again there is this factor, there is this factor, so we will have some numerical factor here, and the rest of the structure is same, 1 over 2m square to the power 6 times lambda square times j to the power 4, which is same as this that we calculated above. Now what about this, which is not matching? Okay, so why is it not matching? Okay, so the reason is this. The thing that we calculated from this Taylor series formula, it actually is a combination of multiple diagrams. So we considered only one diagram here with 2 vertices and 4 external lines, but there is a possibility that there can be other diagrams of this form. Okay, and the sum of all these diagrams should be such that the overall structure is the same, but because we summed them up, this extra numerical factor is there. For example, if let's say this was 8 and we had, let's say, 8 of these diagrams which with all these same properties, and when we would have added them, we would have gotten the same 8 here. So this is because first we are not considering the symmetry factors that I mentioned above properly, and second is that we are summing over all the diagrams of this form which correspond to V being 2 and L being 6. So in the Taylor series formula we are summing over all such diagrams, but when I'm just drawing diagrams, I'm just drawing them. So this configuration, so each configuration doesn't necessarily correspond to only one diagram. That's the main constraint. Okay, so we need a way to organize these diagrams properly. Let me just review what we have done till now. We had an integral which I called z of j, which was this minus half m square x squared plus jx plus lambda over 4 factorial x to the power 4, and we have claimed that this can be written as sum over various diagrams. For example, this diagram, maybe a combination of this diagram and this diagram, some other diagram may be somewhat like this. This is also a diagram with 4 external sources and 1 vertex. We can have a diagram such as this, or this, or we can have a diagram such as this. It also have 2 vertices and 6 external legs, or any sort of combination such as this. Remember, all these diagrams are just numbers that correspond to some certain V and some certain L, or let's say that they correspond to certain number in the Taylor expansion. It is also possible that some of these diagrams correspond to same V and L, while some of the singlets correspond to a certain V or L. So there is just a very messy expansion, and we need some method to somehow organize these diagrams. And here is the key idea, that if you see a diagram such as this is nothing but a product of diagrams of this kind. There is this, and there is this. You can check it explicitly that this is a product, and these diagrams are somewhat fundamental, somewhat like the building blocks of all of the diagrams. I mean, not these, but in particularly, what I mean is the ones that are connected as in you can trace the whole diagram without lifting your pen. On the other hand, this diagram is not connected because you have to lift your pen. This diagram is also not connected because again, and this diagram is connected. This diagram is actually connected on its own. The upper part of this diagram is connected, but due to another external line, it's not connected. So if you consider the connected diagrams, you can see that you can construct the other more complicated diagrams from these connected diagrams. For example, a connected diagram can be this. This can be a connected diagram in this theory. This can be another connected diagram. This can be a connected diagram. This is another connected diagram, and so on. The only requirement is that first it should be connected, obviously, and second that whatever is the vertex structure should be such that 4 lines emerge from the vertex. In every one of these vertices 4 lines are emerging. So that's important. And there are other connected diagrams also. And the more complicated diagrams, such as this one, can be a product of these connected diagrams. So one connected diagram of this kind, 2 of this kind, multiply them, you will get the this diagram, which is a general diagram. And such general diagrams do appear in the expansion. So the idea is to organize things in such a way that we only need to calculate the connected diagrams once, and we are able to calculate the whole expansion without worrying about how and where and what to organize. So this is how we do it. Okay, let's consider this. We need some language to set up the formalism. Okay, let I label these connected diagrams. For I being 1, let's say I'm talking about this diagram. For I being 2, I'm talking about this one. For I being 3, let's say I'm talking about this one. For I being 4, I'm talking about this one. This is 5, this one, and so on. So for every I, we have a connected diagram of different kind. A unique connected diagram is associated with a number I. Also, these diagrams I am calling Ci. For example, this diagram is C1, this diagram is C2, this diagram is C3, this diagram is C4, and so on. Now, let's consider a general diagram D. For example, you can think of this diagram, but let me consider an even more complicated diagram. Now what I'm doing is a bit more abstract and general, so it can be a little confusing at first, but just keep in mind that we are just talking about a diagram of this kind, or maybe of this kind, which is disconnected, which is a product of multiple connected diagrams. So let's say we had 2 of these, we had, let's say, 3 of these, we had 7 of these, and let's say 1 of these, and so on. There can be others also. Let's say this is just one example of a diagram. This is one diagram. What I mean is that this corresponds to some V and L in that infinite Taylor expansion. Some V and L. Okay, we can actually calculate what V is. 1, 2, 3, 4, 5, 6, 7, 8, 9. V is 9 here. So this is a disconnected general diagram, and this can be written as, for instance, this can be written as this diagram to the power 2, but we will also consider symmetry factors here, which means that the number of ways in which this whole diagram can be reshuffled so that this is the same diagram. And this is easy to do, because if I just put this infinity type diagram here and this one here, there are 2 factorial ways to reshuffle these, there are 6 factorial ways to reshuffle these, there are 3 factorial ways to reshuffle these, and there is only 1 factorial way to reshuffle this diagram. So that's why I'm putting a 2 factorial here. And this diagram, the one with X, there are 6 factorial ways to reshuffle this. So this diagram uniquely is this one, times, because remember the diagram was a product of the disconnected one, times this one, which is a line, and there are 3 of these, so I am cubing it over 3 factorial, and then finally this diagram, which is only 1 over 1 factorial. And another diagram could have been a different diagram where we could have another number of these graphs, another number of these graphs, and so on. So a certain graph or a certain general diagram can be labeled by these numbers 2, 6, 3, 1. You can sequentially, or you can properly label like this, as you have set up this list where each I corresponds to one particular diagram. So you can, for example, write a number like this. For this case, we can write that the infinite diagram has 2 copies. The next one, the line diagram, has 3 copies. The next one, which is this weird thing, this has 1 copy, and this X has 6 copies, and this sort of thing, whatever this is. This has 0 copies, and others also have 0 copies. So like this, with the set of these integers, I can label this diagram. From this set of integers, you can immediately construct the diagram. For example, I give you another set of integers, let's say 0, 3, 1, 5, 2, and so on. Okay, let me keep it up to. This set of integers corresponds to a diagram, which means this, that I equals 1, I mean this type of diagram, there are 0 of these. Then I equals 2, 3, this type of diagram, there are 3 of these, so 3 lines. Then there is this, which is I equals 3, which is this diagram, and there is 1 of these, so this. Similarly, 5 of these x's and 2 of these. And this is the diagram, and 0, and let's say others are also 0. So 0 of whatever this weird diagram would have been, and all others are also 0. So this is the diagram corresponding to this set of integers. So this is how we can label diagrams, I mean general diagrams. Our goal was to just reorganize this whole series, this whole Taylor series, or the whole sum, so that we only care about the connected diagrams. So this is how we will do it. So consider the series Z of J, and there are many terms in it. Some initial terms could look like this. Then there are some more complicated terms, and then there are terms of this kind, this. So there is, let's say, some diagram where we had this 2 x's, 3 these, some lines, some of these guys, and so on. Then there were other such diagrams, complicated ones. Then there was some other diagram, let's say this x, there are 2 x's, 7 lines, and so on. So there can be complicated combinations. In general, there can be complicated combinations. And remember that we were identifying them with the set of integers, like I said here, like this one. And similarly, this guy is also identified with a set of integers. So what we can do is this. Now this is the claim. Since this can be written as, let's say, x square. Okay, let me just write this again, this time in that other form. Since there are 2x here, so I can write it as x square over 2 factorial. X is the diagram, which is a number, and times 3 lines are there, so line cubed over 3 factorial. 3 of these infinities are there, so infinity cubed over 3 factorial. Then there is 1 of these weird whatever is this, 1 over 1 factorial. So this is the type of diagram, plus there are others like this. And similarly, this diagram, which is also a example, I mean a type of diagram in the expansion, this is of this form: infinity square over 2 factorial, x square over 2 factorial. Again, these are symbols, not literal infinities. Line to the power 7 over 7 factorial, and so on. Okay, now the claim is as follows. I can write this as follows, that 1 plus line squared over 2 factorial plus line cubed over 3 factorial, and so on, times then the other diagram, 1 plus this infinity diagram plus infinity square over 2 factorial, and similarly infinity cube over 3 factorial, and so on, times the other connected diagram, which is x, so 1 plus x square over 2 factorial. And similarly for all the connected diagrams, I'm claiming that this, whatever this top general sum is, this sum is equal to this sum, and I'll prove, I mean not prove, but at least use a semi-convincing way. Okay, and this will also have the other one, like 1 plus this diagram plus this diagram square over 2 factorial, that diagram square over 2 factorial, and so on. The other, this one will also be there. Similar similar thing, 1 plus this plus. And all such diagrams, connected ones, I mean the ones that are labeled by this I, like this, all these are covered, and more of them are here. All of these are present in this, like the product type thing. So let's say if I, and this is an infinite series of products, and this is also an infinite series. Let's say I want to recover the above series from this step. So if I want to recover this kind of a product, what I can do is pick out this infinity diagram series and use this, choose this one, this X diagram series, use this, and the line diagram series, the term which is line to the power 7 by 7 factorial in this series, choose that. And in this, in the expansion of all these complicated products, there will be a term of this kind which will give me this. Similarly, there should be a term for which I will use x square over 2 factorial. There will be a term for which I will use line cube over 3 factorial, infinity cube over 3 factorial from here, this weird man to power 1 by 1 factorial, and use all these factors in this product expansion that will give me this. Similarly, if I just want this, I will have this times 1 times 1 times 1 times 1 times 1 and so on. That will give me this. And similarly, the point is, any sort of general diagram here or any sort of general diagram here which might be present in this expansion can be obtained in this way by a certain product from this infinite product series. So what this means is that we have converted this weird sum over all these weird disconnected diagrams which were labeled by certain V's and L's. We have converted this into this infinite product, and in which each of these series have a certain diagram. So this had this, the other product one had this, one had this, the other one had this, other one had this, and so on. And all of their structures are of that of an exponential, which means that the first series was e to the power line, the other one was e to the power infinite diagram, the other one was e to the power this diagram, the other one was e to the power this diagram, e to the power this diagram, and so on, all the other diagrams. And this can be summed over. So finally, our integral, which we were after from the beginning, is just e to the power line plus this plus x, all the connected diagrams. So now we don't have to worry about the unconnected ones like this or this. Now what we have done is just rearranged the diagrams such that the final answer is exponential of sum of all the connected diagrams. And this is a remarkable result. We can do even better if you consider the ones without any sources, that is when j is set to 0. So you will only have the bubbles. I mean the diagrams such as these which had j's, these which had j's, all of them will be 0, and only bubbles will remain. For example, a bubble like this or a bubble like this. This one is also a bubble because this also has the same structure. Each vertex has 4 lines coming out of it, or a bubble like this, and so on. So all these bubbles, the sum of these bubbles and exponentiating them, that corresponds to z when j is 0. And we can divide the whole z with this z of 0 to renormalize this whole thing, so that we will just have an exponential of all the diagrams that do not have bubbles or vacuumless. They only have sources in them, like this one or like this one, or like this one, and so on. All the ones with bubbles in them are gone, they have been normalized. So the advantage is that when you put z to be 0 here, you will just have e to the power 0, which is 1, because there are no bubble diagrams left. Or you can think that you have divided z of j by z of 0, which just had bubbles. So you have eliminated the bubbles and only these kind of diagrams are left without bubbles. Okay. So let me just summarize what I have done. This is what I have done. I had this integral which I knew how to solve, z naught of j, and I will also make some QFT references now. E to the power minus half m square x square plus jx. I knew how to solve it. It was e to the power j square by 2m. Also there was a m by root pi here, so that z naught of 0 is 1, the normalization. Then I considered an interactive integral, which was the same integral, but it had lambda times x to the power 4 in it. And let me just also mention that if I had, let's say, instead of x4, if I had x cubed, and I have put a 3 factorial here, just pulled out a constant from lambda. So in this case, the procedure would have been the same. I would have split this in a similar fashion, and I would have a d over dj cubed this time, and all other things would have been the same. And this would mean that now my vertex factors or my vertices would look like this, not like this. This vertex had 4 lines emerging out of it. This vertex has 3. You can think why that is the case, because now the lines are killed by 3 derivatives, and the way to kill 3 lines at once is to form a vertex like this. But anyway, we had 4, and it's interesting to see what kind of diagrams would have emerged from a 3 vertex problem. Okay, one of them could have been this, another could have been this, maybe this is one, because here we have 3 vertex, here is another 3 vertex. These can be source. This is a bubble, not a pure bubble, but a bubble in okay, what else? Yeah, so this we wrote as e to the power lambda over 4 factorial times d over dj to the power 4 acting on z naught of j, where z naught was the one that we could integrate, the Gaussian, which was e to the power j square over 2m square. Okay, maybe I am just messing up m squares and m's, but that doesn't matter really. Here it's m, so it's m square, so it should be m square. Okay, then we Taylor expanded both of these, and we made diagrams associated to each of these Taylor expanded terms, but those Taylor expanded terms had disconnected diagrams. So then after some thought we realized that this whole thing, this whole z of j, can be written as e to the power times some w of j, where w of j is just the sum of all the connected diagrams, which would include this, something like this, something like this, and so on, something like this, and so on. And also we have also eliminated the bubbles from it by renormalizing it, by dividing it by when z is 0. So actually I think I am defining this as omega of not omega, w of j. So all of this is done in QFT as well. In a theory, this is called the partition function. Just that there are some more complications there. For example, for every line we were doing 1 over 2m square. This was a propagator. In QFT it will become some other propagator, for example m square plus box, or in Dirac it would become this minus m, where this is just del gamma mu, or in other theories it would differ. And the structure is same. There also we remove bubbles by renormalization, and after removal of those bubbles there can still be some connected graphs which have divergences in them at loop level. For example, this in phi 4 field, this is eliminated using renormalizations. And yeah, the Feynman rules are similar. In a Lagrangian, this thing is replaced by Lagrangian, and in the Lagrangian also there are like phi 4, phi j, and terms like that. So if there is a phi 4, you can be certain that your vertex will look like this. If there is a phi cube, your vertex would look like this. If you have a phi square, you don't have to worry, because you can, add that or absorb that in your original terms. So phi square is integrable. You don't have to worry about that. In a Gaussian, phi square is doable. Phi cube, on the other hand, is not. If you have phi to the power 5, you have this sort of a vertex. If you have different fields, for example, one is phi, one is some other phi bar, one is some other phi, so you have a vertex. One of them is for phi, two of them for phi, and one of them for phi bar, and things like that happen. So the general idea is the same. Okay, so I hope you liked this video. Okay, I don't know what to say now. Okay, I'll go maybe. If you have any questions, you can ask me.